don't know why many students are not able to come, but so we will proceed along with the revision. So, for example, you are multiplying two matrix. Basically, multiplication, we know that sometimes we are applying the dot product rule in matrix, okay? So, suppose there is a sale price of some product, and of course, real actual cost of the some product. First product R is 316, actual cost is 316, but sale price on your shop it becomes 445, some profit. Actual price 180, sale price is 250. Okay, so you want to know what's the average profit in this month of January, February, March, or you want to observe the sum. Of course, you need to multiply the product with this number of month, and then you will get this product, and of course total sum of element wise product multiplication will give you that in this atom, this R atom is having this profit in January, F atom is having this profit in January, so you will get all along the way. Okay, your Zameen Zameen.com and other properties and other international stock exchange, Bitcoin, cryptocurrency, whatsoever. You are predicting something. You are seeing the possible data, all the past data. Then by with this, this is for your rune, and this one is some another cryptocurrency, Bitcoin or maybe Arduino, or this is the profit, and you bought at this price at the current time. What's the price? And then you see in this month. So you are predicting your data. Similarly, sometimes you want to know the overall cost of some atoms. Of course, these are vectors. Previously, these vectors I portrayed in form of a matrix. Now the simple vector. For example, you are buying some dressing, 2 shirts, 3 pants, 4 hats. Of course, in terms of some dollar value. So this is the value of the 2 shirts. This is the value of 3 pants. This is the value of 4 hats. Of course, you want to know in your computer system, cash machine will tell you total cost become this. Actually, everything is, of course, nowadays we are triggering with the AI, but it is already there. Okay, so this, but we don't actually. Problem is this: we don't know how it works. That's why we cannot develop the basic things. Even we are buying the calculator or other the small tiny machine from the China or some other countries. Small applications, okay. So we notice the artificial intelligence, deep learning, or you can say AI, important, the most basic thing is the data. And once we have data, then requirement is its representations. So every data is arranged in form of vectors, or the combination form of vectors is a matrix, and of course it's following the linear algebra. And of course, once we are having the vector, or we are combining all the vectors together, it gives us some matrix. Problem is not this, we can do it. But problem is this, to analyze, how we can analyze it. Analysis is kind of a vector embedding, and this is some kind of a tricky situation. Basically, it comes in the category of factorization. For example, I'm asking to give me 9 lakh. Okay, to you people, I am requesting, I need to borrow or give me 10. You are, okay, 5 to 6, just for simplicity, maybe you can say that we can give to you in this formation. That someone say I can give you 3 lakh or maybe this metric multiplication or some, okay, you are multiplying with this or sometimes sums. This is the basic factorization of 9. Factorization of 9. Multiple of 3's. So, to analyze this 3 lakh is easy in compared to the 9 lakh. We know 3 lakh multiplied with 3 lakh will give us a 9 lakh. Or just come to small numbers. Small computing of the small numbers is really easy. Similarly, if we have big matrix, means the big amount of problems, our head is fully occupied. We are under pressure. Okay, we cannot sort out the things in a real fashion, in a proper way. But if we are dealing the problem in a teeny tiny step, of course we can get our required or desired solution. As I already told you that if we are standing at the peak of mountain, if we are taking, okay, by jumping, maybe we will hurt ourselves, maybe we will injure, but some serious injury can be happened. But by dealing with little steps, okay, by getting down little steps, with care, we can reach on the ground safely. And this concept in AI, deep learning, is known as gradient descent. That gradient, change, okay, descent with some step by step. I will explain this concept of gradient descent later, but this is the matrix factorization. Similarly, we need to factorize the matrix in terms of lower upper triangle, or you can say singular value decomposition, or principal component analysis. All are these basically what? Factorization of the matrix. Then again there is something which is the dimensions. If dimension is too big, it will really difficult to cover it, to encompass or to observe each and everything in various direction, or in the big direction it is almost very difficult. But if we reduce, okay, the dimensionality, or for example, there are in radar, you want to observe the object in the air, especially during the war zone. You want to localize the army aircraft, enemy aircraft. Maybe there are other small birds or kites are flying, or maybe there are certain objects in the air. Radar will show each and every teeny tiny detail, but you can, by applying a derivative information at an instant. In my first lecture I told you we are ignoring the negligible values just after applying the binomial theorems, and we are just considering the first power of n in derivative. So we are focusing only the aircraft, big object. We are ignoring the small values. Once we are ignoring the basically small values, it is what? Basically we are reducing the dimensions. Okay? In matrix, the negligible, for example, in pixel values, in case of image, some values are too high, maybe 255, 200, but somewhere near to 0. 0 is what representing some kind of a black. And if you can say, here the small objects, if you can ignore it, it's not a big deal. Okay? But this may be some kind of significant information, but if near to this area, you can ignore it. Okay? You don't need to analyze it. And you can transform all small value, maybe these values are 10, these values are 15, 100, make them 0. So your dimensions will be reduced. So dimensionality reduction is also one thing in deep learning for better accuracy and for the fast processing. Basically computational cost is playing a huge role in all the AI and the deep learning work. So if we focus more on the data representation, that how we can do this mathematically and how computer will do it, okay, is the important topic. Idea is basically we are generating each and everything from the vector information. And a moment ago I told you the attributes of a house in form of a vector are the features, values. Okay, so this is the way to organize the information in form of a vector. Once we are having too many vectors, then we can make a matrix. Basically, initial thing is a vector. And once we have some vector, okay, or you can say that vector is a one-dimensional array of numbers. Of course, it is having some magnitude and length. I already told you people with some direction, but direction is kind of our intention. And its dimensionality, of course, if the two-dimensional, three-dimensional, what is in the here, usually on whiteboard we are talking about the two-dimensional thing. Features, I already told you people, if you want to analyze some patient or some diagnostic data, again, AI, deep learning will work only once you will have nice, precise information of the, in case of patients, there are three attributes, three values. Of course, you can give, with the passage of time, you are observing some patients, you are family patients, or you are visiting some family doctor from your age, at the age of 10 to the age of 30, gradually you are becoming grown up, so of course he will keep the record, your weight record, your age record, your height record, then there will, are you getting my point? So three-dimensional data. And once you, okay, so the values where you want to stacking up the some values, for example here 0 to 255 in something, all the values can be assembled in one vector, okay, in one array, or you are stacking up. The purpose of stacking up is this: you are considering the high value at the top and low value at the bottom in order to kick them out from the system. So here you can notice that it is not only to the images. For example, you are searching some information on the Wikipedia. Of course, you will search too many pages, okay? Or you want to notice that you are looking for some particular article or some particular information. Maybe one or some, okay, on Google pages or Wikipedia pages, they will give you the complete information. Some will only give you the one point of it or 2 points of it in that article. You will ignore. Usually you ignore, that will provide you the very limited information. You are clicking or you are opening, or the only that page which will give you the huge number of your words or your required information in a complete order. Okay, so the reduction of dimensionality is the same thing. You are ignoring the less sufficient information. And the order of this is that it's in your rating or not. For example, it's not up to your desired level, of course you will ignore it. You will give it a low rating. But it may be possible. So one say that it is better than me, other say, for example, a person like me, say I am old, too much food is not good for me, but some other good player, athlete, he need a good energy, and of course he need a very good food. So something maybe no for me, but for other, yes. Okay. Sometimes we are dealing with non-numerical data, for example, languages. Okay, and some, of course, the languages in our country, there are huge number of languages. After 5 to 6 kilometer variation in languages will be happened. Too many varieties of Pashto, too many varieties of Hindko, Punjabi. So there is some non-numerical data, you can say, can be noticed, and this non-numerical data can be done with the help of one hot encoding. And one hot encoding is basically what? Basically is a standard benchmark kind of a matrix, kind of a vector. A moment ago, for translation purpose, for rotation purpose, I have shown you people the benchmark matrix. Here, similarly, for non-numerical data, we are using the standard basis vector. Basis vector, let's come to the point, basis vector. For example, if you are talking about the apple, okay, apple, you are considering some standard basis vector, and in this standard basis vector, you can say if you are talking about, this is a limited amount of data. Here, remember, we are talking about data. In this data, you feed it that first, okay, if computer vision in the vegetable market or in the some shop, it is noticing the apple, it will click on the first one. Of course, pictures with huge data, its system knows what kind of a shape, what kind of a color will apple have, so it will click apple. For cat, say this is the basis vector. Other values all will become 0. Only the second will be highlighted, it's one binary system information. In case of house, it will show third one as a one value. In case of a tiger, last one. But problem is this, what will happen? Apple, totally different things. Cat, different thing than the apple. House, different thing than the apple and cat. But if we see cat and tiger, almost 2 eyes, okay, kind of a skinny thing, 4 legs, they almost similarity, then matching, okay, nearest possible things can be done. Confusion matrix can be created here. So, in this scenario, okay, language, okay, words of the language, so some can be mixed up. Then it's the problem in this one hard encoding, our machine can be confused. Okay, so in this situation, if you can notice that here tens of thousands of words, too much vocabulary, too much different variations. In that case, we will confuse the machine, or we need to see the precise system for this purpose, and this purpose that each word, okay, we need to make a, here we are talking about 4 words, so 4 elements in one vector, 4 attributes. One is highlighted, others are 0. So we need to generate a vector with 10 of thousands of words, 10 of thousands of attributes values, where for one it will 1 and the other will, its dimension will be 0. So these are drawbacks which is happening only and only due to similarity reason. We can overcome these drawbacks with the help of usually dot products. In start of the lecture, in second lecture, I have shown you people that we should do this with the help of dot product. We sum up the information, we need to categorize it. And this dot product, basically what we usually do, we are noticing the reverse engineering. Basically, if we want to analyze something, all the AI, all the deep learning or machine work is done. First we extract the information and we reverse, apply it in a reverse way. For example, we want to see some numbers and factorize the number, factor of 10 are 2 and 5. Okay, so we see we have 2 vectors. In these 2 vectors, if we are we are generating 2 vectors, and number is almost near 7 is near to 10. Like cat is almost similar to the tiger. This is the problem that, okay, though not exactly the same, but the situation is this, the nature of dot product will tell us about the things. Similarly, here we have some numbers, we are getting some output in form of a 4, though it may be exactly not equivalent to 10 or not equivalent to 7, but 4, but almost near to it. Not 95, not 200. Once we are talking about 10 of thousands, we are talking about million of words. This is frequency is almost near to it. So it can be matched. So if you are talking about the basically similarity comes from the shadow. okay, shadow. Okay, that is the, you can say that it is kind of image of it. And this replica, you can say that we are taking the dot product, we are multiplying both hours. Check out the output. Output is what? It's almost similar, closer to the which one? For example, there is a 10 and there one is a 7. And there are two vectors we are multiplying, and output is near to the 1, this one, or near to this one, 7. Are you getting my point? A moment ago, here we give this, and of course in form of a vector. Okay? We factorize it. After factorizing, we are multiplying in form of dot product. Then output is equivalent to which one? The near to the 10, or will tell us the near to the cat, or will near to the tiger similarity. Here you can see the vectors, and this vector is some kind of a shadow, and you can say you are multiplying this shadow with the original one, and check out what will be the output. Dot product. And sometimes here you can see if we are multiplying the apple and cat, answer is what? 0. And this one you can say is the, you are multiplying the tiger and cat, again 0. So though there is no similarity, these are the totally different things. Okay, apple and cat are totally different. Are you getting my point? Totally different. But in technical, if we are at far-flung distance, we are capturing some images with the help of camera, we could not categorize a cat is look like a tiger. Because we are, distance matters, okay? Nouns, length, can say, oh, it's the smaller size. Maybe it's a tiger, but maybe we can say a cat is look like, okay, the same pattern, same zigzag, okay, on the, in the, maybe in the dark we are capturing the image with the grey pattern, we say, oh, it's tiger, it's cat, we cannot categorize it. But system say there is 0, no similarity in it. Sometimes gives a huge similarity. This is done 0 because these two hard encoding. Okay, but similarity measured with the help of dot product. This dot product say, oh, no similarity. But without dot product, it can be similar. See how important this linear algebra. Dot product after two vectors, cat is having some attributes, 2 eyes, 4 legs, some kind of attributes. This cat, and this say it's cat. Tiger is having this kind of attributes, so we are multiplying both. So this is no similarity. It only tells system, computer. But with simple you can say naive approach, say it can be a cat or it can be a tiger. But once machine say, hey, machine final confirm answer, no, not. So it's maybe machine can be wrong. Similarly, in the medical diagnosis, it gives us the. But in all this situation, what is the important solution is what? Better vector representation. If vector is having maximum number of attributes, too much features, each feature is will be compared and will be, okay, in dot product it will tell us that answer is what? In a right direction or in a wrong direction. So the idea of embedding is, of course, in the smaller dimensional space, the faster computing or the, you can say, efficient, for getting efficient result. And key point is this: if we are having the dimensions of 3, we need to reduce it to 2 dimensions. Okay? How, my children? See, we are slicing up the brain or the CT scan in form of with the help of gamma rays. We are getting a volumetric information, too many frames. But clinical expert will observe the correct information. How? By observing the, see, if we are having the 1 frame, 2 frame, 3 frame, so it becomes volume. Okay, too many images. However, clinical experts will do analyze first one, then second one, then third one, and each time basically will observe the 2D case. One image, then second image, then third image. Replacing here, this is the 3D, so we just pile up the data. Pile up the data by considering we have A4 size paper print page. Usually its width, thickness of the paper is negligible. Okay, just you can say one dimensional. Maybe length and width, or sorry, its thickness is negligible. If you are piling up A4 size paper one another too much, thousands of paper, you will see some volume of it. So this is, we are observing the volume in case of slice, single frames. Okay, and then one single frame slightest thickness, then it becomes a 2D kind of a one page. So, as I told you people, the embedding system, first one I already explained to you, the factorization one. Factorization, sometimes once there is huge things, or you can say too much numerical data kind of a language, it will give us a complexity or the problematic. Though simple is, like in case of images, some matrix factorization work, but not very high and accurate. Then in that case, what we will do, we use the neural network, where the logic gates, decisions, OR gate, AND gate, like will work. Okay, first see the matrices. If we are talking about this, I already explained to you, stretching, rotation, scaling, something not more complex, but simple. Okay, now you got the concept of this, and you will get your desired output. So this is already the things we do. We transform from the 3-dimensional to 2-dimensional. This is not a big deal. Your matrix factorization, we can increase the scale by scaling the vector. Okay, for example, magnitude, we increase the double of the magnitude of a given vector. We can make it half smaller size. Similarly, we can rotate it. We can translate it from one position to another position. There are certain possibilities exist. So sizes of matrix, of course, this is the 3x3 matrix. You want to shrink it to the 3x2, then of course you need to multiply with some benchmark matrix or some small size, so you will get output in form of a 3x2 instead of a 3x3. So sometimes we are getting the output, and the given final output, big data, is the multiplication. What we notice in the nature, that we are getting the multiplier final output, and but for analysis purpose we need to factorize it, decompose it. Okay, and of course it's the reverse way, like China is doing reverse engineering. So this is matrices can be factored by using the SVD, singular value decomposition. Any of you familiar with it? Singular value decomposition? No? Oh, okay, I try to explain it. This is very useful thing in huge number of applications. If it is possible, please check out on the Google what's the singular value decomposition in AI, maybe some YouTube or some Wikipedia information. It's a very good concept. In technically, every matrix can be factorized, can be decomposed. In cryptography, we are the encrypted data here. Hackers are hacking the websites. What are they doing? Basically, they are, if it is easy to factorize, then they can easy to hack the system. Are you getting the point? Very simple, but very interesting also. So this is the basically concept of the factorization in form of a SVD, singular value decomposition. One is the big matrix. If there is a number of row, you can say 4 to 5 are like this, and you can see different smaller size of matrices, 3 matrices, each